Welcome everyone. My name is David, and we're here to talk about voice-activated AI collaborators, like a hands-on guide to using LLMs in IoT and edge devices. Hopefully this is going to be an interesting thing. We're going to have a demo at the end. I'm going to do it live. We're going to do an air-gapped one so that you can have it completely contained on your IoT edge device. And then we'll have other variations where we can go out to the internet and offload certain things. So hopefully you'll find this a very interesting talk. So yeah, my name is David Von Thenen. I'm a software engineer, developer advocate at Deepgram. I have been working in the AI and ML field for almost 2 years now, specifically in NLP, so natural language processing and conversational AI, so like summarization, that kind of a deal. Previous to that, I was doing a lot of stuff in the Cloud Native Computing Foundation, so the CNCF with Kubernetes. So doing a lot of container runtime, storage, workload orchestrations like in Kubernetes, right? We're moving containers around within a Kubernetes cluster. Prior to that, I was working in the backup and recovery solution space for virtualized environments, specifically vSphere, but also in like cloud and public cloud as well. Also a lot of storage. I like to do a lot of automation. I like to work with public cloud providers. Here's the agenda. So we're gonna go over what a voice-activated AI collaborator is, just kind of like the level set, like what are we talking about? It's pretty much what you think, but I hopefully throw in some things that might be different. And then we're gonna go right into the meat of the presentation here and just talk about like IoT and edge design considerations. So specifically, we're gonna talk about 3 things, although there's like a ton of things to consider. One's obvious, right? Resource constraints on an IoT edge device, right? There's limitations on how much you can pack in such a little tiny space. And then we're going to talk about speech, LLMs, and running possibly multiple models, so multiple machine learning models on your device. So talk about all of that, like different ways of doing like hardware acceleration, and then we'll kind of like wrap it all up, kind of give like a summary of like how you might best pick what things you want to bite off in your device and what things you might want to defer, or if you want to go for the full shebang and like have your device be self-contained air gap, you can do that as well, and I'll have a demo of that. And then we'll kind of have some Q&A. So yeah, let's talk about what is a voice-activated AI collaborator. So just like what you think, it would be like, I've had pictures of common ones that we deal with today, right? Google, Siri, Amazon Alexa. At a very high level, right? You speak, you say something, a command, an instruction. The device, whatever it is, does something, and then you get a response back in English, right? Or whatever language you want to pick. And it will give you the result, the answer, confirmation of that command. Here are some things that are like future that are now, right? So like MetaQuest, the Apple Vision Pro. People might not be familiar with the one in the center, but it's the Rabbit R1. So just because devices have, maybe controllers to control like your interaction with whatever device that you have, always be aware that there could be secondary interfaces to your device. So instead of just using your controllers, like in the MetaQuest case, you could also integrate like voice activation and voice recognition to say, hey, do this, or kick that off in conjunction with like using controllers, right? So just always keep that in mind, that like one of our most powerful interfaces with talking with other people and also devices is just spoken word, right? So just keep that in mind. The cool thing about, like, if you're not familiar with the Rabbit R1, its primary interface is voice. So it's basically you touch it, you speak your command, it goes off. I don't know the exact implementation details, whether it goes in, I assume goes into public cloud, does something, and then returns a result back and gives you whatever it is you wanted to do. So if we kind of like double click into like what I just said, what makes the device an interactive voice assistant? The first part is you say something, and then you take that speech and you do something, and then you talk back to the user. So that first part is that say something. What is actually happening is you need to have something that understands speech, and something that understands speech and converts it to text, right? And once you have a string, like in the programming world, now we can actually do something with that. So the first component is speech to text. You'll hear many different variations of it, automatic speech recognition, transcription. They're all basically the same thing. And since we're talking about talking to a device in real time, we're talking about real-time automatic speech recognition. So now once we have a string or some translated sentence, phrase, paragraph, whatever it is, we want to pass that off to an LLM, right? Typically these days it's an LLM. Previously, like I think Amazon, the Alexa, Google Home, they weren't, right? Because that came kind of a little bit after. So they did, some very interesting things where they are actually triggering off keywords and then running off and doing stuff like that. That's why it would always prompt you in the morning, say good morning, right? Those were like key phrases that it would trigger off of. These days, we're using LLMs, right? We're using machine learning models to do things, to interact, go analyze video, understand what we're saying, and then third piece is we take that result that comes out of that LLM and then we convert it to voice, right? So that it can speak back to us and give us an answer in the language of your choice. So that's kind of like really like the high level flow. If I break it down, speech to text, go through an LLM, possibly multiple LLMs, and I'll actually talk about that a little bit later, different machine learning models, and then take the output, that text output, and go back to speech, right? So you can verbalize it and have a speaker, which we'll do a little later. So yeah, this is kind of just the summary of that. So I kind of just threw this in here so that you have something to reference like later after the talk here. It just kind of summarizes exactly what I said. I'd like to point out a couple interesting things. When you talk to your device and it talks back to you, it doesn't necessarily have to come out of a traditional speaker, right? If anyone's using like bone conductive headphones, it's like that little thing that sits behind your ear and it uses vibration to like give you the sound of what you're hearing, except it's not all like audible to everyone in the room, right? It's specific to you. Conversely, this is actually kind of very interesting. When you speak, it could be a microphone like I'm using today, or it could be something like The Thing, which is very interesting. I would encourage you to click that link later. It's actually an analog microphone that was used to use vibrations that Russia used to spy on the ambassador to Russia, and they used this thing, which was an analog mic, to actually pick up vibrational frequency to understand and like eavesdrop on like what was being said in that room. So I'm just keeping your mind open about all of the different modalities or the inputs and outputs that you can use on a device, right? It doesn't necessarily have to be a speaker or a microphone. It could be video. Now let's talk about, now that we kind of have an idea about like what our device can do, is capable of doing, video, audio, but primarily we want to talk to it because it's a great interface. So let's talk about now how we want to, all the considerations that we have with IoT and edge devices, right? Like all the constrained resources on a particularly small device. If we do have a small device, you can only pack so much into that device. You can only put so many CPUs and so many cores in there. You can put only so much memory. These days, you can actually put like a GPU and a graphics accelerator on there. A lot of it is, yes, you can play video games on it too, but the other use case is also to run machine learning models on there, like LLMs, to accelerate the performance of the feedback, to the user. And then you also have storage considerations, like how much storage do I need to put on this device to like land something very, very large, like an LLM on there. And then like network connectivity. So you have to weigh all of these things, right? There's all these variations of like storage, memory, whether you have a GPU or not. And you really have to understand and think about like what your use case for your device is, right? Like what are you trying to accomplish? What do you want to do with this particular device? And then when you kind of dissect the device and you say, this is what I want to do, now you have to start to allocate the resources you want in order to accomplish that said goal, right? That particular use case. And while all that's happening, right, yes, you want the device to run absolutely as fast as you possibly can, and you can throw everything in the kitchen sink, 500 CPUs, well, I mean, doesn't exist today, like 4 CPUs, 16 gigs of memory, a GPU accelerator, the best network card, best microphone, best speaker, but now it starts to drive the cost of your device way up there, right? And an individual might not want to purchase that device because it's too expensive. So you have to like weigh all of these things when you're deciding like what things you want to have in your device. So like I said, you have to understand the problem that you want your device to solve. And like I said, the microphone isn't the only input. You could have, voice commands that like kick things off, but you could also have things like a webcam for like that does, maybe 480p, 720p, whatever it is, as another source of input for your device. And so we call that like multimodal, right? So we have voice and we also have video. It could have many other things. Maybe it goes out to the internet to get information. Like whatever it is, you have to consider all of the things that you're going to do in this device and the problem you're trying to solve in order to decide what you want to do. So other use cases and goals, if you want your device to be intelligent, remember history. When we interact with like Google, Google Home, Siri, you say something, it gives you whatever it is, the weather, it's sunny today, and then you go to the next question. But if you ask anything about history, about like what was the weather that I just asked, tell me what it is, it's not going to understand, right? It's usually right now, currently, it's very discrete. This is the question, here's the answer. I can't go back and give you history, the historical information that I gave you. You could make your device do that, but it requires a little more in your device, right? It requires memory, a database. If you're talking about an LLM, you might actually be talking about like a vector database so that your LLM can learn and store that information. So you have to ask these questions in order to figure out like what your device needs to do. And just because you want it to do everything, you might want to consider how good is good. So like what is good enough, right? If your device can be, I don't know, $50, $100 cheaper, but maybe there's a 1 or 2 second delay, is that good enough to give you a lower cost on your device, right? Maybe it's cheaper, the barrier of entry to buy it is lower, and so more users might buy your device, right? Kind of a deal. And it doesn't have to be in a commercial thing. I'm just using that as like a means to like understand the cost. If you're gonna like mass produce these, it's going to cost you a whole lot to manufacture these devices, as a part of your solution. Again, it kind of comes down to like what's the minimum viable product. And you really kind of want to achieve balance in like all of those things, CPU, GPU, memory. So I just kind of would, to illustrate and also kind of like touch on another subject. So this is like kind of like a graphical representation of like a very high performance kind of a device. So you could have a lot of CPU. Maybe it has 2 graphics accelerators, like 2 GPUs. Maybe it has a lot of memory, disk, and maybe that's enough. And you want it to have that device just be self-contained so that it's air-gapped, so that it doesn't go out to the internet, so it's completely secure. That's totally cool, totally an option. And maybe you do want it to connect out to the internet. Maybe you have some infrastructure in some public cloud where you want to, I don't know, send some telemetry or like do logging or whatever it is, right? Just understand that that's always an option, right? It doesn't have to necessarily be closed off, but if you want it to, you can. And if not, the internet and having network capabilities in a lot of cases are available, and in some cases not, right? It just depends on like what that use case for your device is. And then on the far extreme, right, we had this super beefy, powerful device. This is like the lightweight, like I don't want to spend a lot of money on making my device. Maybe this device has just enough to run, right? A CPU, enough memory to boot some embedded operating system, a microphone so that you can actually talk to it, right? Because we're talking about voice-activated AI agents. And maybe you want to defer everything to cloud, right? So you basically have API calls calling out to your infrastructure. It's doing all the processing up there and it's sending you the results back over the network. Maybe that's okay for your use case, right? So just consider that you have 2 extremes, like the very expensive device and the very cheap, like in the computing world, like a thin client, right? It's enough to get what you need, have it be done somewhere else, and then have that data be sent back. But kind of in the end, you kind of want like a balance, right? Somewhere in between those 2 things. It could be way skewed in one direction or it could be way skewed in another direction, right? You might want a little bit more on your device just so that there isn't any lag and so that it can process things locally a lot quicker, and like what workloads it's going to run, because it always comes back to that. Like, what do I want it to run? How fast do I want it to run it? Like, what is this going to cost me, like, to build this thing, right, with this kind of hardware? Keep throwing in these recaps. So if you want to take a look back later, right, lower thin client devices are going to cost less because the hardware is, you don't have as much hardware, or you could have a very beefy device where you have GPUs and all that kind of cool stuff. So now here's, I think, where we're going to get into something a little more interesting, and I try to get to this really quickly, hopefully, because I think this is where it's a little different. So if we're going to do speech, LLMs, and machine learning models on an IoT edge device, we got to talk about those considerations, right? And so we're going to talk about a lot of these. And the 3 topics that I kind of wanted to highlight, one is transcription accuracy. So when I say something, how accurate it is that's going to like record, like, and take the sounds that are coming out of my mouth and build sentences and words out of, right? How accurate is that? Then the second thing is, since we're talking about an LLM, how that transcription is going to affect the prompt accuracy, right? Like, what is the result that I'm going to get out of the LLM based on the accuracy and like the input for the prompt that I'm going to give the LLM, right? And then the last one's kind of like this outlier. It's kind of different than the first 2. But it's, if you're going to run multiple LLMs or multiple machine learning models on your device, like, what does that look like, right? So we'll kind of get into it a little bit later, but I've already said there are 3 like machine learning components: speech to text, LLM, and text to speech. Technically, those are 3 models, so we got to kind of talk about that, right? When we're building a voice-activated AI assistant, like, the minimum that it needs to do is understand the words that are coming out of your mouth, do something, and then give you a result back in, verbalized in like whatever language you want to do. Based on what kind of device you have and like what the market is, who your users are, it's going to determine how accurate that conversation is going to be, right? If you, it's whether your device can tolerate errors, right? If, as an example, if you have like, your Amazon Alexa or whatever device it is, the device that you've created, and it can't transcribe things very well, and it gives you an error or gives you some form of information that's not related at all, like, it's no big deal, right? You can ask the question again, and maybe it'll get it right the second time, right? Maybe there's some other noise in the background that was interfering with its ability to do the speech recognition. Now, if this is a medical device, now things change quite a bit, right? Because now the accuracy of what you say is kind of important, and hopefully everything's fine, but it's so important that someone's life possibly could be on the line for it. Or maybe it's a doctor who's doing your device is some form of like note-taking for your doctor, and the doctor, it doesn't transcribe things exactly right. Now it starts to make a lot of difference in like whether or not that transcription is accurate or not. I've been talking about the first part, right? That first component, that speech to text, and why we care about the accuracy of the transcription. I kind of threw this on here because I think everyone's had this problem on their phone before, right? You want to do the texting feature and you don't want to type it out, and you say something, right? We've all had this problem, and then you're like, oh my gosh, what the heck, right? But in this case, no one cares, right? No one's getting hurt. You feel stupid, obviously, but it's no big deal, right? You type it out and you say, oh no, I meant this, right? So just, if you're going to compare these different speech to text models, just gonna understand like what the word error rate is. So it's basically a term. It's a calculation of like how accurate that transcription is. And so like if you have a word error rate of 20%, that means that the transcription was 80% correct. So you want a lower word error rate. So if you had a word error rate of 10%, that means your transcription was 90% accurate. And so this is what you use to measure whether or not like this particular transcription application, platform, library, or whatever is better than this one. And it depends on also what your domain is. In the medical sense, you might need more medical terms. And so you have to compare like to like things, right? So just, understand that's how you can quantifiably measure accuracy for transcription. I threw this other one in here. I'm just going to pass it by. There are more links if you're interested in more funny stuff at the bottom. Like, why am I talking about word error rate, like how accurate a transcription is? So here is an example, and I have the source at the bottom, of a transcription of a podcast where they're talking about like how excessive use of vitamin D and vitamin B6 can, lead to like vitamin toxicity. And I have on the left-hand side, yes, the left-hand side is, I've taken those texts, I've taken that actual transcription, like the correct one, the 100% correct human transcribed transcription, and I've passed it through a summarization AI, and I've taken another one, that same podcast, and I've sent it through an automatic speech recognition transcription platform from a popular cloud provider, and I also sent that thing through the same summarization AI. And passing it through the AI, you can see the summaries here and here. The very interesting thing is, because the transcription is so poor on this popular cloud provider's transcription, it missed a lot of things the summary of this particular podcast was. And the very interesting thing is it missed out that like vitamin D, because it wasn't transcribed correctly, that it completely missed that vitamin D was literally the focus of this podcast, and taking too much vitamin D is very harmful for you, and you shouldn't do it, right? But it's kind of very interesting to see like how that transcription can have massive downstream effects, like when you're talking to other machine learning models. So I used summarization because it's it was AI driven. And if we're going to use what we're saying as a driver for an LLM, that means that we're going to effectively take what we're saying and use that as the foundation for our prompt for our LLM. And so if the transcription isn't that accurate, that means also our prompt for our LLM is not accurate as well, right? It has holes in like what was captured and what you want to convey to your LLM. And because, if you think about like what an LLM is, it's effectively boiling it down to something very simple, although it's not really, the oversimplification of it is that, LLMs are like next token prediction engines, right? They're using like what you're saying in the prompt to match up with the result that it wants to provide you, like the answer. Now, if the tokens, in this case, are words, sentences, and phrases, if it can't get those tokens because they were initially bad to begin with, when it's parsing when it's tokenizing what you're saying, you're not going to get anything meaningful as an output because the initial input was bad. And so this is kind of like seeing the effects of like how transcription can have massive downstream effects to an LLM. So this is how like prompt accuracy can like literally go out the window because the initial data or the prompt that you're providing is bad. I've taken that, using that same vitamin D and vitamin B6 transcription, both from the actual one and the second one is, through going through a popular transcription from a popular cloud provider. I'm not going to use names. But I've taken both of these transcriptions. I've created a prompt which basically says, you'll be asked a series of questions regarding the content enclosed. Use this content to drive your answers from, and do not use any external data information, right? We want to keep all the information self-contained. So I've taken the actual transcription on the left and the poorly transcribed one from the cloud platform on the right, and I asked the LLM, it said, sure, ask away. And I asked the LLM, are there any specific vitamins that are being called out in this article? And so the LLM I used is ChatGPT. And ChatGPT was able to identify that vitamin D and vitamin B6 were called out in this particular podcast about, like overuse of prescription, or overuse of vitamins can be detrimental to your health. And the one on the right didn't even mention vitamin D at all, right? So if you're now starting to like use this content as like the formation of questions that you want to ask, now it starts to look very, very bad, right? So another example, I said, ask ChatGPT, was there any mention what could have caused the uptick in these vitamin overdoses? From the actual transcription, it was able to identify that COVID caused a significant amount of overuse of vitamin D and B6 because people thought that you could, beat COVID using vitamins. And, it led to a bunch of, basically the podcast was saying, not my opinion, I'm just saying the podcast said that, a lot of people are getting sick because of, vitamin overuse because they thought that it could help with COVID. And in the other side, right, ChatGPT from the other poor transcription wasn't even able to get that at all. It was basically gave you a generic response, an answer to that particular question based on like the information in this podcast. Other questions, you can kind of see the story that it starts to paint, right? So if the transcription is not good, downstream effects can be very, very not good, right? And so it's kind of like shows the importance of using, like having accurate transcription based on like what you're doing. So if you have if you're doing stuff that's medical related, then use speech to text platform service local model that understands medical related things, right? Because that then increases or decreases your word error rate and increases your transcription accuracy so that you can feed into your LLM. So those are, so hit the first two. So transcription accuracy, how downstream can affect prompts for your LLM. And that's kind of this weird outlier because, and then something we have to address, right? If you're going to run multiple models on your device, you're going to have to figure out ways of doing that. One really easy way that you can just literally throw money at the problem is get a GPU, right? You can have a GPU on your Raspberry Pi. So an example like the NVIDIA Jetson TX2, I think it's like $200 now. I mean, it's really not that bad, all things considered these days. Like just having hardware acceleration on your IoT or edge device can literally give you a 4x performance boost on, running machine learning models and stuff on your device. So it's actually quite significant. You can not have it, and the speed that it's going to give you the answer is going to be whatever like CPU you have on your device, right? It is going to be what it is, right? So there are different ways of like dealing with that. You could potentially, if they're like smaller models, maybe you can just load them as you need them. Maybe if these models are pretty beefy, maybe you have them running the entire time and you just take the memory hit that is required to like stand this thing up in memory and just like let it live throughout the life of the device while it's being powered on, right? So that you can minimize the startup time, shutdown time, and so that it's always accessible, so that it's always, you can just query it and you get an answer back. If you are going to use hardware acceleration, I just would throw some things out here that the way by default, like if you're going to use NVIDIA and you're going to use like CUDA, right? By default, when you offload your machine model workload to like a graphics accelerator, specifically CUDA and NVIDIA, it does it in serially, right? So here's a problem, you go, crunch on the numbers, give me the response back. Here's a problem, crunch on the numbers, give me the response back. And the reason why I'm calling this out, because if you're using a speech-to-text model, an LLM, and a text-to-speech, those things are going to be in serial. So you're talking about like a weird kind of single-threaded kind of a thing, right? Speech, problem-solving, answer, right? Now, different ways you can handle this. So if you want to have the ability to have memory and you want to work on multiple things on your device at the same time, most graphics cards have the ability to earmark CPU or GPU cycles for workloads. So like as an example, NVIDIA has something called multi-instance GPU, which effectively you can say, I want to take this GPU and I want to divide it into thirds so I can run 3 workloads in parallel. So I can run my speech to text, my LLM, maybe I have 3 LLMs, and then your text to speech. And so there are ways to like mitigate certain things based on the hardware that you have. And so I'm just kind of calling this out. I'm sure there are other GPUs and AI accelerators that have very similar things. I'm just using NVIDIA as an example. Kind of the point is like you have to think about like all of these models as kind of little services. They provide small little capabilities, and you can run as many of them as you want, depending on the hardware that you have, right? The other thing that I'll probably mention here too is if you have multiple models running on your system, the middle piece, right? Not the speech to text or the text to speech. There's like mechanisms for combining multiple models to give you better results, better answers. As an example, I actually just thought about this the other day. I was trying to, what's a great example for this? So maybe you have 2 models, like the first one's a medical model, and the second one is an LLM. And the first one is like you do the speech to text, it does the transcription, whatever it is like some medical related, tell me about this particular drug and like what it does and like what are the side effects and this, that, and the other. And the medical model is going to spit out a very specific medically jargoned, like whatever it is, probably very detailed that some doctor would be like, oh yeah, okay, cool, check, I totally understand that. And maybe you can take that output and pass it into an LLM to do explain it to me like I'm 5, right? Give me the more general version of what this thing does so that I, as a non-doctor, understand exactly what what the restrictions are and that kind of a thing. You could be running multiple models as an example in your device, right? It's called Ensemble Learning. I put a whole bunch of links in here. There's other things for doing like running multiple models at the same time and doing voting and weighting the responses for certain models so that you can combine them in order to determine which one is which one's the better answer, or combine them to give you a more accurate answer. So they have this whole thing about combining multiple models. Believe it or not, you can actually, depending on the models, you can actually run them on an IoT or edge device. Like this could be a whole nother talk. If you're interested in running multiple models, not just an LLM, I put a whole bunch of links in there, so it's like some homework you can take a look at. We're going to take all of this stuff that I've talked about, and we're going to like wrap it up and kind of like talk about like how now we have all this knowledge and how we want to like build your device, coming to like a final kind of a design. So like I said, voice assistants will require minimally 2 models. These days it's probably 3. The speech to text, LLM, text to speech. Keep in mind the problem you're trying to solve. Your device is probably, obviously it's dependent on the speech to text and the text to speech, but that's probably not the primary goal for your device, like it's just talking to you, right? So that middle piece, that LLM piece is your logic that's going to define like what your device does, right? Maybe it does something medical related, maybe it does something else. Keep your eye on the prize. Like what do you want to focus on when you're problem solving, like what your device wants to do? So the reason why I bring this up is, could you build all of these 3 things? For sure. Definitely can be done. You can use off-the-shelf components. You can, like open source components. You can use platforms that you've stood up in a public cloud. You could use maybe even public APIs, right, from like, a cloud provider. You don't necessarily have to solve all the problems. You can choose to use other platforms that are out there in order to accomplish the same thing. And so like when I go back to those graphics, you don't need to run, as an example, maybe the text to speech on your device. Maybe make an API call, which is literally a string that you want to verbalize out to public cloud, and then get the like MP3 file, like what you want it to say through a speaker. Maybe that's a better solution than trying to land a model to do the text to speech, right? Because that round trip time isn't that bad. and compressed audio, and then you're providing input as a text, right? Text message, right? You know, be conscious of like what battles you're fighting. The meat of your component or your IoT or edge device is that middle piece, that LLM piece. The battles you choose to fight on your device, right? Whether you want to stand all three of these models up or not, right? It's going to determine how costly your device is going to be, right? If you're going to try to run 3 models, you know, don't use the lowest end CPU for your device. So just be aware of like what you want to focus on and what things you can defer out in order for your device to be the cheapest, but also something that your users are willing to tolerate, right? Like what's the cost to benefit ratio for building a device like that? Based on like your domain language, you know, a lot of speech to text platforms allow you to help define your own vocabulary. So there's like things to do that, but kind of the overall point of all of that stuff is like defining your own vocabulary, using a medical speech to text model. It's to get that accuracy, right, the word error rate lower so that your transcription's more accurate, so that your prompt to your LLM is better, so that you have a better result in the end. You know, if I say this out loud, it's gonna seem super obvious, right? You have a function, right? The input, if it's messed up, the output is probably going to be messed up too, right? So that's kind of like the upshot of like this whole thing. Yeah, maybe like another example, like in the multimodal example. Here, this is just kind of like another summary slide, but maybe your IoT edge device has a webcam and you're doing 480p. Do you really want to like bite off doing like an LLM and process video on your device, right? Maybe you're doing some sort of video capturing thing where you want to do license plate recognition on cars, right? Do you really want to spend the time and burn having an LLM sitting on your device, right? I've been advocating for LLMs this entire time, but maybe you make a call to some public cloud provider's LLM or something that you've stood up in your own infrastructure, right? Just to make the GPU on your device completely 100% dedicated to that video processing. So that's kind of like what I'm saying is like, you know, pick the battles that you want to fight in order for your device to do the best that it can do, right? Find the bottlenecks and apply your hardware to the best possible location for the problem that you're trying to solve. I'm gonna do a demo, several demos actually. You don't need to write any of this down. At the end of my presentation, probably tonight, maybe tomorrow morning, I will tweet out the slide deck with all of the links so you can click them to your heart's content. I have taken literally all of the assets that I used to build this demo in my GitHub repository, which we're actually going to go over right now, all of those things kind of. The link is here for the GitHub repository. It literally has the different speech to text, text to speech, the LLMs that I use, like the open source ones. I've even gone as far as, you know, the poor transcription example with the prompt that you feed in the ChatGPT, that's all there too. So you can get the exact same prompt. The AI, the summarization AI that I use to summarize the podcast is all there, and we'll actually take a look at that right now. So like I said, it's all in the GitHub here. This is like the folder for it. If I do an LS, you can see literally it broken down by the section. So just to kind of give you like a overview of it. The AI summarization, so if I just did like a Python main, I've dropped in the conversation text over there, which is probably not legible at all. If you run the Python script that's here, and my cool notification that I'm going out to the internet, which is going to be important in a few seconds, I had to accept OK so that it can access an outside resource on the internet. This is going to give me the summarization that I used in this particular talk. So you have access to that. So other things, like the speech to text, I have an open source version here. It's Pocket Sphinx. It's actually kind of very cool. If you run the main that's in here, how are you doing today? How are you doing today? Notice it didn't give me the pop-up to access the internet. So it's completely air-gapped. Text to speech. If you go to...
I will speak this text.
Right? Completely air-gapped. I mean, it's not the best sounding thing in the world, but maybe it's enough for your device, right? I'm giving you like the extremes of this is not running an LLM. This is literally doing speech to text using sound waves and analyzing them and, spitting it out, and vice versa. The text to speech is also like that too. Now, what I wanted to show you actually is this. And I'm going to start it up here. And everything comes with a README, which basically shows you exactly how you can start everything up, like install what you need to install to get this thing running. What I'm going to run right now is OpenLlama locally on my laptop here. I'm going to put a REST interface on top of it so that this model's always running. And then I'm going to run a script, another Python thing, which is that, yeah, there we go. This is probably going to come out horrific, but we'll have to wait and see. So this is basically I'm going to talk into the microphone. Hopefully it's going to transcribe things correctly. I'm going to pass it through that OpenLlama LLM that's running locally on my laptop. It's small enough to fit on an edge device. It's under 4 gig, definitely enough to fit in memory. You're definitely going to need enough memory to run it, but it will run on an edge device. And then it's going to speak back using the speech to text and then the text to speech that I just showed you in those other examples, right? So let's see if this is going to work this time and cooperate. How are you, dude? How are you doing today?
I'm here to help you with any questions or tasks you may have. How can I assist you today?
Okay, at least got part of it. How many planets are in our solar system?
I apologize, but I'm a large language model. I cannot fulfill your request to make the world darker. It is not within my capabilities or ethical guidelines to manipulate the physical environment or cause harm to live.
The fun stuff of running things locally, right? So notice that I didn't get the pop-up for my firewall to say, go out to the internet to do all this. So it was running on my laptop. So now let's take something a little more interesting and complex. So maybe you don't want to run the models. Maybe you want something a little more accurate. And that's kind of like weirdly the point, right? Pick and choose your battles, find out where things are better in other places, right? So if we're going to run a speech to text and a text to speech that's not on this device, we're going to get my pop-up from my firewall. I was trying to go through this thing. Thing doesn't have a speaker. How are you doing today?
I'm doing well, thank you for asking. I'm here to help you with any questions or tasks you may have. How can I assist you today?
How many planets are in our solar system?
Great question. Our solar system consists of 8 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Would you like to know more about any of these planets?
Yay! Okay, so you can see that it's actually going through, right? This is where it's getting the reply back. Now the really cool thing about this is this OpenLlama thing, I have a REST interface on top of it. What I actually did was, the REST interface completely mimics OpenAI. So if I do this, kill this service here, without changing any code other than, go out to hit OpenAI instead. How are you doing today?
Thank you for asking. I'm doing well, ready to assist you with anything you need. How can I help you today?
So I've given you many examples of, this would be like the thin client example. I'm not running anything on my device. I'm hitting OpenAI, I'm hitting other services to do the speech to text to speech. And in the first one, although the transcription didn't work really well for me, completely air-gapped, right? And everything in between. So that's kind of like the point of it. All the code is to do all of this is in my GitHub repo. And yeah, that's my talk. Hope you found it interesting. Questions? Do you have a URL for the slides? I will tweet it out. I don't, but you can follow me here. All my socials are there, so D. Von Thenen on LinkedIn, on Twitter, on GitHub. Send me a message, however you want to do it. Take a picture, follow me, friend me, whatever you want to do. If you have any other questions after this, I'd be more than happy, after this, to answer questions. Shoot me a DM or whatever.
Yeah, I was wondering, since this is kind of the embedded track, did you play around with quantized models to try and reduce the amount of resources and stuff like that at all? And can you talk a little bit about that?
Yeah,
Experience with that?
I did, and so the Open Llama that I ran was actually a quantized model to reduce the amount of resource to fit on there. I didn't do it myself, although you can use tools out there like Llama CPP to do that for you. I have a link to the model that I used in this demonstration, that 4 gig model. You can literally, I'm not even joking, download the model, drop it on wherever you want, and literally run it just like I did here. It's the 7B. It's the 7B quantized to reduce the amount of resource that it needs so it can fit on a device.
And did you have to change things? Did you have to change the way that the Mac is allocating the memory? Because I think the Mac uses a shared memory pool between the CPU and the GPU. Did you have to change the settings to give it more GPU memory?
On here, I left it exactly as is.
Okay, and can you tell us how much memory you needed for GPU or CPU, or for the GPU, I guess?
I don't have the exact numbers, but I believe I believe the LLM was 6 gigs of memory, to be running. And so if you had something roughly at about 8, because of the 2 speech to text and the text to speech, because I wasn't running models there, it was basically, you're not taking a CPU, a huge CPU or memory hit, right? And then, like I said, if you want to defer things, call out to an LLM that you have running in your public cloud infrastructure or whatever, you can totally do that as well. But yeah. No, definitely. Everything in the demo in the repo should fit on an 8 gig edge device, like a Raspberry Pi 4. I forgot what model I have, but yeah, that's what I used to test it and stuff. For sure, 100%. Yeah, I actually have instructions to run Falcon on here, so it's not just the Open Llama one. So I have the Falcon 13B, I think, is on here. So I have the instructions on how to run that as well. And I also have Llama 2, in case you want to do something different. That one's not running an API server or REST API server on the front end. It's literally standing up locally, asking the question, shutting it down. So I have all of these variations in my GitHub repo that you can play around with. Yeah, cool. Anyone else? Yep.
For running on the edge, have you tried some of the TPUs that run at they're not quite as the floating points. They use the smaller floating point, and they run so you have to massage the LLM.
Yeah, I personally haven't, but yeah, I would definitely. The only one that I've really played around with is mostly NVIDIA related stuff, and it's mainly because yeah. So the one that I was trying to purchase it before, and I was hoping to have everything on my Raspberry Pi that I had, but I didn't get all the stuff in time, unfortunately. But that particular Jetson TX2 NVIDIA card, it's $200. It attaches to a Raspberry Pi, so you can literally have it in that kind of a form factor, and then offload all of your.
That one, I've got the Corel, but I haven't tried it myself either.
Yeah, so I haven't tried some of the other ones. It's I probably should just foot the bill and just try it myself.
Well, they've dropped in price.
Yeah, so they've significantly dropped in price. So that's it's
doable now.
It's totally doable as like a hobbyist enthusiast kind of a thing. But yeah, I haven't personally, but definitely encourage if you're interested about performance and benchmarks to Google it. There's a lot of people that are doing all this cool stuff and and publishing results. I definitely encourage you to look at that. Yeah. Cool. Anyone else? Cool. Well, thanks. I have fidget spinners, stickers. Take as many as you want. Take them all. And then I don't have to take them back. Thank you.